Hello everyone, Assalamu alaikum. I'm Esan, and in this series of videos that I will be making for this capstone final project playlist, I would be covering the entire work that was performed for the capstone. As you might have already noticed that I have uploaded two videos regarding the evaluation and the pitch idea for our capstone project, and for this series I was thinking of analyzing and organizing the work that we perform for the capstone and present it accordingly, right? So on the screen what you are seeing is the overall big project of the picture in the form of poster presentation. So it is something that I will go into details later on, but before we do that, I would first make a video about how to set up a rapid prototyping or a hardware loop setup using the Simulink. Right, so I will first give you a brief idea of what our project is all about, and then we will jump on to the systematic and step-wise videos as to how the work was performed and what were the results obtained from it. Right, so for our project, we basically demonstrated a rapid prototyping technique, which is a hardware in loop technique, or a FPGA in loop technique, which is used to design, test, and deploy controllers, converters, or any model onto specific hardware that is not designed for that purpose, but can replicate the working and functionality of the desired model. For example, we have a model of a motor or any kind of plant that we designed in Simulink, and we want to test its functionality when we implement it on actual hardware. So the cost of building an actual hardware is obviously quite a lot. So what we do instead is that we um, deploy that Simulink model on an actual simulator, or a real-time simulator such as FPGA, or it could be a microcontroller as well, or we also have real-time simulator hardware dedicated to replicate the functionality of the Simulink model that we designed. Right, so for this project, what we chose as a model was bidirectional DC-DC converters, which were implemented completely in the simulation or the Simulink environment. And to control these converters or bidirectional DC-DC converters, the controller that we were designed was something that we deployed on the hardware. So the reason for deploying the controller on the hardware rather than keeping it or leaving it in the simulation environment is to basically demonstrate the actual functionality of the controller when we will deploy it in real time on the converter that we have designed. And the specification or the parameters that we chose for the converters, both for the non-ideal and ideal idea sorry for both the isolated and non-isolated, were in the context of electric vehicles. So I would also discuss in detail. So on the right you are seeing the big picture of the project, which we basically so this one right here on the top right corner was the work that we performed in the POC one, or the proof of concept one, and on the um, bottom left, or what we have is the work that we performed during the POC2. Right, so I will go into the details of both of these models and the rapid prototyping or our FPGA loop setup for both of them in a separate video. But for this video, I want to particularly focus um, on the setup of our entire work. Right, so I would start off by Simulink tool, and we would then proceed as to see how the FPGA loop setup can be organized and can be used to um, design and deploy hardware as per our need. Right, so we used these two great tutorials given on the MATLAB owns website, where they have covered in detail as to how we are supposed to set up the hardware which we want to replicate our model on, and how we can put that in loop in order to test the functionality of our designed plant. Right, so this one right here, a block generation with FIL wizard, is particularly for FPGA or FPGA loop setup. So the steps that are given here are specific for the case of FPGA only. So in order to set up the hardware loop or FPGA loop environment within the Simulink, um, Simulink MATLAB, what we have to do is we have to first of all have a compatible version for the MATLAB, as well as the as well as the synthesis tool that we are using. For this particular tutorial or for this particular project that we conducted, we would be using Xilinx Vivado. So we will first have to see the compatibility of the MATLAB version that we are using with the Xilinx Vivado. This can be found on their in their manual as well as their website. They have provided a list of compatible versions for Xilinx Vivado and MATLAB. So once you have these two things installed, the next step is to link the Xilinx Vivado that we have with the MATLAB, and for that the following two commands can be used. If the synthesis tool is Xilinx ISE, then this particular command would be used, and if it is Vivado, then this particular command will be used, right? So so first of all, I will just quickly use this command to set up. Since I'm using MATLAB 2017, I have also installed Vivado compatible 2017.4 versions, so I will just replace that and will set up the environment path for the Xilinx Vivado. Once that is done, the next step is to ensure that we have the right packages, MATLAB packages, and for that you would need to install the following: MATLAB support for MinGW, C and C++ compiler in case you are using Intel FPGAs, and you have to install Xilinx Zinc platform embed coder support package. So the reason I have installed it is because the FPGA that we used in our project was Z-board, and it is a Zinc based platform, so this one was essential. And additionally, you need these three of HIL coder support package, HIL verified support package, and HIL coder support package for Xilinx Zinc platform as add-on, and also these right, and this additional HIL verified HIL coder support package. Right, so these are the must to have add-ons and support packages in order to perform the hardware loop testing using the FPGA setup, using MATLAB or Simulink setup. Right, so once you have installed these packages, these mentioned one of this one, and these three of HTL coder verifier and support package, and additionally the HTL coder and HTL verifier, the next step is to set up the FPGA. So for that purpose, I won't be going into the details of the of how the FPGA should be connected and should be interface with the MATLAB, but HTL verifier support package provides functionality for that, and you just have to go through all of these steps that they provide. For example, since I've used Z-board, so I've selected Z-board here and it is interfaced with my simulation environment using a JTAG cable. Since Z-board only allow interfacing using the JTAG cable, so follow this step, and if the FPGA is connected or is interfaced with the MATLAB successfully, then it will simply give you a thumbs up, or otherwise it would mention the error that it faces during the interfacing. Right, so once you have done that and the FPGA is identified with the MATLAB, and you have also installed the compatible MATLAB and Vivado setup, and have interfaced the two and have installed all of these packages, the next step is to test whether these installed setup is working correctly. And for that you can by the way, the HTL verifier steps that I just showed you can also be replicated using these steps, where you have to manually obtain the IP address of the FPGA, and then you have to verify it using these given steps here. But that is quite redundant and a long process, so I would suggest that you use the HTL verifier to perform the task. Right, once that is done, so additionally MathWorks also provide a simple example in order to test the FPGA loop setup, whether you have done it right or not. So for this purpose, they have the example that they have given is a PID controller of a motor plant, and for that they have given the following model. So for this model, the DC motor plant is implemented within this block, and then we have the controller block. So the entire model would be running on the in the simulation environment, except for the controller part, which would be running on the FPGA or on the hardware of your choice. Right, so I would go through all of these steps as well to show you how to generate a FPGA compatible block from this particular HTL compatible block, and then we would then replace it and then verify the results. Right, so first of all, they have also given the couple of steps in order to set up the FPGA, which I told you about told you earlier on, whether you can use IP address in order to set it up, or you can simply use HTL verifier in order to set up the FPGA. Secondly, I also told you how to set up the HTL setup toolpath in order to link the Vivado and the MATLAB. And once we are done with that, we are good to go in order to load our model and then test its functionality. Right. So moving on to, so the rest of the steps I would simply explain in the example on the MATLAB itself. Right. So this is the model that model example that that MATLAB has provided. So for this particular model, the entire model is created within the simulation environment, within the Simulink environment right here. Uh, um, and also the DC motor model is simply given by its state is by its dynamic equation, and then we have these digital to analog converters and the data type conversion blocks in order to find a compatible data transition between the FPGA and the simulation environment, because since FPGA is a digital it is a digital device, so the data that has to be transmitted it has also is also supposed to be digital, and for that we need to convert our data type. For example, regardless of what your simulation environment is working on, the interface or the JTAG interface that is provided by the FPGA with the simulation environment is only 4 byte or 32 bit wide, so we have to ensure that the appropriate data conversion type is also used. So this is something that will have to go in the manual for, and you'll have to um, understand how the data types work and what kind of compatibility has to be achieved in order to successfully ensure uh, uh, the data transition between the FPGA and the simulation environment. Right. So this is the given model and this is the controller part. So what they have done is that they have designed the entire model here, and for the controller part they have used the HTL compatible block. So the HTL compatible block are something that are only HTL HTL convertible, meaning if I convert this block or this block right here into HTL compatible block, it might not be possible because they were not designed with the HTL compatible block, unlike this controller block. So you have to either go through the manual in order to verify how the HTL compatible block works, or you will have to simply just do trial and error. So it's better that you identify which blocks are HTL compatible and then design your model accordingly. So for the controller part, they have implemented the PID controller, and all of these blocks that you are seeing here are HTL compatible, meaning we can generate a compatible HTL code for these blocks, and which can, with the code or the bit stream that is we have generated, can be deployed on the FPGA to perform the in loop testing. Right. So for the PID, they have selected the gains right here, which you are seeing. For the proportional gain, we have this constant block right here. For the integral gain, we have the integral gain, and then we have the integral integration constant, and then similarly we have the differential block. Right. So all of this entire part is HTL compatible, meaning we can generate a successful HTL compatible block for or FPGA loop block for this particular setup. Firstly, what you have to do is you have to verify the results as well for your model that is completely running within the simulation environment and no FPGAs involved. So for that, you will have to run the simulation and capture the results. Right. So if I open the scope right here, so as you can see, these are the results that we have obtained entirely from the simulation environment. So we have the desired position and the actual position corresponding to that as per the design controller. Right. So again, this is the example that is given to us by MATLAB. MathWorks. So MathWorks MATLAB, and the gains that they have selected is giving us this desired result, which is quite accurate enough if we compare to the desired position, this actual position that we have obtained using the design controller. Right. So once we have these results, you have to either capture them or just remember them, and the next step would be to design the FPG compatible block and then test the results again. For that, we will just right click it and we'll go to HTL Workflow Advisor. Right, and you will have to go through all of these steps in order to generate the FPGA loop block. Right. So once you have interfaced the FPGA Vivado and the MATLAB, it should automatically detect which Vivado with this HTML word query device should automatically detect which Vivado version you are using, and would simply load it here. So I'm using Xilinx Vivado 2017.4, so it has detected that, and you'll have to go and check through all of these steps in order to generate the block. So let us do that. So the target frequency would be identified automatically, so you don't need to change whatever it is written here. Um, in case there is any error, which might be the case when you are designing the HTML compatible block from the scratch, so what you need to do is that the HTML workflow advisor will give you some suggestions in order to improve that error, and you just have to simply follow those advice or the steps in order to remove that error. So for this example, we already obviously don't have any error because it is provided by MathWorks itself. But in case such an error, any error would arise, it would Azure Workflow Advisor would give you appropriate steps in order to correct that error, and you should do that accordingly. So I would just run through all of these together because there isn't much to discuss in each of them. Similarly, we would have all of these. Right, so for this command, check generate RTL code in test bench would generate the HTML code for each of the blocks that we have for our FPGA block setup. Right, so once we have that, the next step is to set the FL options, and for that we would simply, the folder that we've selected would have this folder created HTLPRJ and HTL source and FIL PID, and all of these files would be generated once you have run this command generate RTL right here. So you simply have to open them, and you have to simply verify them by clicking run this task, and their compatible VHDL file would be verified whether it is whether they are error or not. So you can see that it is compiled successfully, and now we can simply run this task in order to generate our FPGA compatible block. Right, so this synthesis of the code that we have just generated for the individual block is going to take some time, and I would pause the video and I would resume it once the block is generated, and then we would see how we can replace the block and verify our functionality with the results with using the FPGA loop setup. Right, so I'm resuming this video as the FPGA block synthesis is just completed. So once you would run this final command, build FPGA loop, this synthesis will start up, and the code that is generated for each individual HL block would be synthesized, and this entire synthesis would be performed in order to generate this particular window right here. So in this particular window here, you can see that for the model that we had previously, this one right here, a corresponding FPGA loop block is generated, which would be deployed on the FPGA. So next step is to simply save this file somewhere. So since I'm just giving you an example, I won't be saving it, and I will just copy this block right here and would paste it in my actual model that I had. And all I need to do now is I need to just simply disconnect this block right here and simply connect the FPGA in loop block with the, or replace the FPGA in loop block with my previous controller design. Right, so now this model, when you would okay, so there are two more steps. So you will have to deploy the file that you've generated. So this controller bit file would be generated automatically after you have run the synthesis, and you will have to define the signal attributes as well as to what your sampling time would be, and the data type um, over the bus. Since we are using JTAG, so we will be selecting 32-bit bus width. Right, once you have that, you have to simply load the file on the FPGA, and when you will press this button load, you have to ensure that FPGA is up and running and is also connected or interface with your simulation through whatever cable, either Ethernet or JTAG you are using. And when you do load it, the FPGA would give you some signal in form of LED. For example, Z board turns on this blue LED when a file start loading onto it. So you have to perform this loading task, and then you will have to press OK. Since I don't have the FPGA at the moment, so I would just simply tell you the step that you have to follow Next, once you have that run, once you have that file loaded on the FPGA, the next step is to simply run the file and then to observe the result. The results that you observe should be very similar to the one that you obtained without the FPGA loop block. Okay, and once you have the results similarity, you can ensure that the FPGA loop setup is working fine, right? So since we are obtaining the same results, so that calls for the cause as to why do we need to even use FPGA in the first place, since we are using the since we are getting the same results from both the setup. So for this particular controller block, it was relatively simple enough, and there was processing involved. It was a simple PID controller. But if our model gets complex enough and we start incorporating more complex and complex algorithms for our controller for a plant, the processing time gets greater and greater, and simulation environment enough is not sufficient to cater or to be robust enough to that processing capabilities, and we need an external hardware in order to perform those processing advanced algorithm processing for us. And in that scenario, FPGA in loop setup becomes very, very important. For example, if you have a AI based or a AI based algorithm or a fuzzy logic algorithm where AI is involved, there would be tremendous amount of processing capabilities that we would require in order to for the controller to perform robustly, right? And for that purpose, we would need the FPGA loop, right? So this was it as far as the FPGA loop setup goes, as to what steps needs to be performed, and how they have to be performed, and the final results or the final verification that you have to identify, um, right? Right, so this was as far as the setup goes. Also, with this video, I would be attaching my capstone final thesis document, in which I have covered in rather great detail as to how these steps have to be performed and what requirements you need to match in order to perform the FPGA loop testing. So you can go through this thesis document, and you can simply replicate these steps after understanding them, and to perform the simulation in loop FPGA loop simulation. Right, so this is, I think, I would keep it to here in this video. And since we have discussed how this basic setup has to be performed in order for the work that we do, and in the upcoming videos I would be sharing you the actual work that we perform in using this hardware loop or FPGA loop technique that I just explained to you how it is done, right? So till then, I would you uh, you can go through the thesis document, and then come up to the follow-up videos in order to see how the um, in order to get familiarize the work that we perform, right? So in the next two videos, I would be discussing each of these setups individually alongside with their mathematical modeling and the results that we obtain from it, using the simulation as well as this poster document right here. Right, so I hope you found the video insightful and informative. And if you do or have any questions, so do let me know in the you via the email or in the comments below, or and do go through the link below to get the files for these videos and to perform this setup yourself. Right, so I will see you in the next video. Khuda Hafiz. Bye.